So, we were talking about tensor products yesterday. Let us recall the definition. So, let M and N be A modules, F be as many copies of A as number of elements of M cross N. Then let D be the module generated by be the submodule of F generated by E x1 plus x2y minus x1y minus x2y E x y1 plus y2 minus E x y1 minus E x y2 E a x y minus a times x y E x a y minus a times E x y x1 x2 x is in M, y1 y2 y in N, a in A. And let D be so let us write T as F mod D. So, given any bilinear map, a bilinear map, F from M cross into P, where P is an A module, given any M cross N to P, F induces a map F tilde from F to P, okay, which vanishes on D so therefore, there exists F prime from F mod D, which is T, to P, or in other words what we have now is that I have given such that F prime of the image of each x y is equal to F of x y. Okay. This is in. So, let us set this notation. The image of E x y in T, this is denoted by x tensor y. These are the generators of T. This is called tensor, we call it. Yeah, we will come to that. So, the main motivation is precisely what we said in the beginning, that given a bilinear map, okay, from M cross N to P, there exists a unique module in which it filters through.
What exactly do you mean by filters through?
Filters through is, so if I have a map so this is I have m cross n to p. So we are looking for in some sense universal module which depends on m and n, such that given this I have a bilinear map which is, so this should be a natural map, and this is a map that induced by f such that this diagram is commutative. Okay. So this such existence of such a module that gives, you know, studying the structure of T, one can say about m and n. Similarly, given m and n, one can study the structure of T, and you know if we go little forward, we will see that this construction looks so unnatural, but the modules that one obtain, they are very, very natural. Okay. So the construction was probably, I mean, if you look back the history, the construction was done after realizing what the module is. Okay.
G here will be a homomorphism.
Yeah, we are going to talk about what G is. Okay. So we have now, yeah, this is what we are looking for. Okay. So define, there is a natural, you know, definition G of G from m cross n to T, G of mn, G of x comma y equal to, there is a natural way, right? G, this induces a map into f, x comma y going to E x comma y, and from f there is a natural quotient map, x comma E x comma y map to E bar x comma y. E bar x comma y, I am denoting it by x tensor y. So there is a natural map from m cross n to T, which I will denote this by x tensor y. Then this is a map from m cross n to T, then G is a bilinear, right? I look at where would x plus, sorry, x1 plus x2 comma y be mapped to? This will be mapped to x1 plus x2 tensor y. I mean, this is E bar of x1 plus x2 comma y, but we are modulo d. Modulo d, this is E of x1 comma y plus, I mean, so this minus, that is 0. So therefore this is E of x1 comma y plus E of x2 comma y bar, which is same as x1 tensor y plus x2 tensor y. And similarly on the other variable, and we have, and a also, I mean the scalar multiplication also is taken care of similarly. G of ax comma y is ax tensor y, but modulo d it is same as a times x tensor y. So therefore this G is an a bilinear map from m cross n to T, and by definition f prime composite G is f. Right? by definition that is how we have constructed f prime, that is how we have constructed G. So by definition we have this map f filters through T. So what we have done is we have produced an A module called T, and we have produced a bilinear map G from M cross N to T, such that given any bilinear map F from M cross N to P, I have a map from T to P such that F prime composite G is same as F. Okay. So this property is called the universal mapping property. Given any F bilinear map from here to here, there exists a map from this to this such that, so this is already there such that this is commutative, this diagram is commutative. You start from here, go via this, or this is the same. Okay. Now what we are interested in, whether this, can we have several, so we have, in this case we have constructed a T. Does there exist any other module with the same property, that given any bilinear map from here to here, do we have a module here through which it filters? So let me let's see what happens in that case. Sorry, f prime is well, f prime is not bilinear, bilinear in this sense, in the sense that, so if I think of this as two variables, then it is bilinear. Now I mean usually bilinear is talked about when you have two coordinates, but well, this is also said bilinear. So suppose I have, I mean what we are trying to see is the uniqueness of T. So suppose there exists a T prime, there exists an A module T prime and a map G prime from M cross N to T prime, bilinear map, a bilinear, such that given any a bilinear map, F from M cross N to P. So I have this is T prime, G prime. So this is F prime. There exists F prime from T prime to P such that F prime G prime is equal to F. Suppose you have another module T prime which satisfies the universal property, universal mapping property. We want to say that this is T prime is isomorphic to T. Okay. So how do I say that? See, these two, both of them are defined using a universal mapping property. Okay. So we have T prime is defined using this property. There exists a module T prime with G prime, a map from here to here, A bilinear, such that any such map filters through T prime. So we can replace this by our T. So consider the map. So we have two pairs, M cross N to T prime. So this is our G prime, this is our G. Okay. So first we have proved that this is our T, which is F modulo D, and this is T prime is the module that we have assumed which exists with respect to this property. Okay. There exists this module such that given any A bilinear map from M cross N to an A module P, there exists F prime such that the composition is F. So therefore our aim is to see if I have a map here and a map here. So let us take the first whatever we have proved here, take this to be P. Okay. Given this G prime, I have a map from T to T prime, take P equal to T prime first. Okay. Then there exists a map, let me call this J, from T to T prime such that, so this is J such that J composite G is same as G prime. By taking this is we obtain this map J by taking T and P equal to T prime in this diagram. Now take P equal to T in this diagram. What do I get? And take this to be, this map F to be equal to G. So we get a map J prime from T prime to T. So this is J prime from T prime to T such that G is equal to J prime composite G prime. Is that clear? So therefore now look at these two. Putting G equal to this one here, what do we get? We get J composite J prime composite G prime is G prime, and J prime composite J composite G is same as G. See now look at this G and G prime. G and G prime, take any x cross y, x comma y to x tensor y. X tensor y. So what this says is that J composite J prime acting on x tensor y is x tensor y for every x comma y in M and N, but they are the generators of the module T is generated by these elements. So therefore this says that J prime composite J and J composite J prime are identity maps. Which means J and J prime are isomorphisms. J is isomorphism and J prime is the inverse of that. which means T and T prime are isomorphic. Okay. So, therefore, let us write down what we have proved so far. Okay. Let M and N be A modules, then there exists an A module T and an A bilinear map G from M cross N to T such that for any A module P and a bilinear and an A bilinear map F from M cross N to P, there exists a map F prime from T to P such that F prime composite G is same as F. Moreover, such a module, if there exists another pair, another module T prime, an A module T prime and a bilinear map, A bilinear map G prime from M cross into P T prime such that for any A module P and A bilinear map F from M cross N to P, there exists a map F. Okay, so maybe I will use this H. There exists H prime from T prime to P such that G prime composite other way around, H prime composite G prime is H. Then if there exists such a map with this property, then there exists an isomorphism between T and T prime. Okay. So, this element, this module with this property is uniquely determined up to isomorphism. This module is so usually denoted by this T is usually denoted by M tensor N. There are nice properties of this tensor product. To start with, see, note that this M tensor N in M cross N, every element is of the form x comma y, where x belongs to M and y belongs to N. But here not all elements are of that form, right. We are, see, how did we construct this? We looked at F for each x comma y I had a basis element exy. Every element f will be a linear combination of elements of exy's. So therefore every element here will be of the form some linear combination of x tensor y, okay. So M tensor n, this is summation ai finite linear combinations like this, where ai is in A, xi is in M and yi is in n, and n in finite linear combinations of this form. What this says is that if this is and I have two generating sets are generating sets for m and n respectively, then this is a generating set for M tensor n. This x tensor y, we will, I mean, let me just take some note some properties, then I will take one or two examples. We will see that this M tensor n is it has slightly different meaning than what not just f. See, in the f we are just taking a free product of all as many copies of m cross n r, but here when we are taking modular relations it becomes it becomes very different. We will see, we will come back to that, okay. So if this is if these two are generating sets for m and n, then this is a generating set for M tensor n. So this says in particular, if m and n are finitely generated, then so is M tensor n. See, even if m and n are finitely generated, the module f that we were looking at is far from being finitely generated, right. In general, see, if you look at this f was direct sum of as many copies of m cross it like this. Even if your module m and n are finitely generated, this is far from being finitely generated, because there are each element is a generator, right. Each exy for x comma y in m cross n is a generator. Finitely, say for example you take z modulo z, I mean sorry, z over z, this is generated by one element, but if you look at in the so if your m is this also equal to n, then the free module f will have as many generators as elements in z, which is also same as z cross z. So this is far from being finitely generated, this is a huge module, but when we take modulus in nice situations, the module also becomes, the tensor product also becomes nice, okay. So this in particular if m and n are finitely generated, then so is M tensor. Now, another remark, this is, I would say, slightly unexpected when you see this for the first time. In the case of vector spaces, okay, if you take a module, if you take a subspace and take any vector there, that vector has a very precise meaning or unique meaning, whether you consider it as an element of this ring, I mean this subspace or the original space, right. But that is not the case for modules. For example, if I take, say, in the case of this is an element X tensor Y in M tensor N, okay. So, this may have okay. So, let me just write like this: if M prime and N prime are submodules of M n, then M prime tensor N prime is a submodule of M tensor N. But now, okay, let us look at one example. Okay. Take A equal to M equal to Z and N equal to Z2, okay, and look at the element 2 tensor 1 bar in M tensor N. Because of the property in tensor products, this is equal to, I can write it as 2 times 1 tensor 1 bar, which is same as 2 times, sorry, 1 tensor 2 times 1 bar, which is 2 bar, which is 0. But this is okay. So, this is one thing. Suppose you take in M tensor N for any x, this is 0. I mean, so I have this representation, this is 0 as the additive identity of the module M tensor N. How do you see that? This is equal to x tensor 0 plus 0. By properties of tensor product, I have this is x tensor 0 plus x tensor 0. This is same as this. These are all elements of the module. So, add additive inverse of this on both sides, use associativity to say that 0 is equal to x tensor 0. So, if you look at this element x tensor 0, that is 0. Yes, 0 tensor y is also 0 for every. Sorry? Yes. See, if you take for example, you take z mod 5z, okay. What is 5 bar? What is 10 bar? Okay, yeah, they are all different representation, that is all. Okay, these are all different representations of 0. So this is 2 tensor 1 bar is 0. Now I take the submodule m prime equal to 2z. Sorry? No, I am taking m prime submodule of m in 2z. Now look at this and n prime is same as z2 itself. I look at, then this is there in m prime tensor n prime, right. Can we do the same thing in m prime? See, 2 tensor 1 bar, this I cannot write like this in m prime tensor n prime, because this is not there, this element is not here. So this equality does not hold in this module, this equality holds only here, not here. So therefore this is not equal to 0 in m prime tensor n prime. So in this case, exercise, list the elements of m tensor n. You will get a hint on this when we do the next exercise. I have Zn, I have Zm, okay. So let us look at Zn tensor Zm. Okay. What would this module be? So let's start with Z2 tensor Z3. So let's look at the element 1 tensor 1, but here this 1 I can write it as 3 minus 2. This is 3 bar tensor 1 bar minus 2 bar tensor 1 bar. What can you say about this element? This element, what is 2 bar? 0. This is, and this is, this is 0. This I can write it as 3 times 1 bar tensor 1 bar. But this I can send it to the other side and say that is also 0. Right?
You could have directly written 1 bar cross 1 bar as 3 bar cross 1 bar.
Yes. Okay, in this case, yes, yeah. Okay, I wrote this because of now Zn tensor Zm. Do you have some idea about this? M minus n is in one look. If you look little more carefully,
So m minus n or n minus n depending on.
well, even more general. What is that we are using here? See, if I can write 1 as a linear combination of m and n, then I can keep n in one side, m to the other side, and say that both of them are 0. And what is that property? GCD of m and n are 1. So if GCD then I want to say that this is 0, right. How do you say that? You take any x bar tensor y bar, this I can write it as x times 1 bar tensor y bar, but 1 bar is some x times 1 bar is some Pn plus Qm tensor whole bar tensor y bar. This is same as xpn tensor y bar plus xqm tensor y bar. This is 0 already, this we take it to the other side and say that both of them are 0. So in Zm cross Zn, Zm tensor Zn, you can make all the elements 0. So now think about this exercise. List the elements of in this case. So okay, let me just write it as Z tensor Z2. Okay. M tensor n means I am in this example. That should be pretty easy now. Think about it. We will. So what happens if Zn tensor Zm if GCD of m and n is D? Okay. Think about this. This is left as an exercise. Okay. Think about this. What module is this? See, this is again a Z module. This is a finitely generated Z module, right? So it has to be something that you can easily express. So think about it. What should this be? We will come back to that later. Okay. Will it be D? I can write it as linear combination of this. So what if there is no D? I mean, so okay, think about it. Okay, there is. It's not difficult at all. It's easy. Think about it. You had something similar in the case of ideals. So now let's look at one or two properties of tensor product. So what we have seen here is that an element is 0 does not mean that it is 0 as element of every submodule, but there is a corollary of the construction that if summation ai xi tensor yi I from 1 to n, this is 0 in m tensor n, then there exists submodules m naught and n naught of m and n respectively, such that summation ai xi tensor yi I from 1 to n is 0 in m naught tensor n naught. So there exists some submodule in which this is 0. That is easy to see, because if you take this summation, this is 0 means it is in D if you look at so you can take it is a finite linear combination of elements of D. So take all the first coordinates and define m naught to be the module generated by those first coordinates and n naught to be the module generated by the second coordinates. Okay, so let me just write one of the basic properties of tensor product, that if I take so property A tensor M is isomorphic to M, that is A tensor X mapping to AX, this is an isomorphism. Yeah, sorry, no, this is 0. There exists a module where this is 0. See, earlier what we saw is that if this is 0, then that does not imply that this is 0 in every submodule, but here we are saying that there exists a module in which this is 0. Okay. There could be modules where this is non-zero, submodules with this being non-zero, but there exists at least one module in which this is 0. Yeah, so this is, you have again all these, you have a map from M to M cross N to M tensor N. Okay. Now if I take a submodule K and look at, so I have this map and I look at phi inverse of K, it is a submodule here. Similarly, I have N to M tensor N, M cross N, N to M tensor N. I have, this is phi, this is, call it psi. So psi inverse of K will again be a submodule of N, okay. And then now think about whether, so if I call this to be M naught and this N naught, check whether M naught tensor N naught is same as K, whether this is indeed the case, okay, and see how we constructed the module M tensor. Well, so okay, I will think about this proof. See, whenever we have to prove something like this, how do we prove that? We have to use the universal mapping property. From here to, so A cross M, I have a map to M, this filters through A tensor M, okay, and we are saying that this, the map A tensor M going to A M is an isomorphism. How do I say that this is indeed the isomorphism? Okay. Think about it, I will do that next time.